Okay, so physics, let's get into it. So let's start with, like, say, for example, number 11, with the softball player sliding into second base. So here's your setup, here's second base, here she comes sliding in. Now, here literally, let me give you some general words of advice. Every problem can only go one of two ways. An object is going to speed up, or an object is going to slow down. That's it, okay? That's what the acceleration is. And the first thing I want you to get out of your mind is that acceleration means that they're speeding up, okay? No, stop. We've talked about this before. If an object is accelerating, all that means is that their velocity vectors are changing. Their velocity vectors are getting bigger, they're speeding up, their velocity vectors are getting smaller, they're slowing down, or eventually we're going to change the direction of those velocity vectors. Okay? That's it. Those are your only three options. Don't ever say the word decelerate, because that just gets confusing. Okay? So when you look at this, so she's going to come, and she's initially going 4 meters per second. Okay? That's when she begins to slide, 4 meters per second, right? So one of two things is going to happen. As she begins to slide, either her velocity vectors are going to get bigger, or her velocity vectors are getting smaller. Now, Carson, what's going to happen?
She's going to start to slow down.
She's going to start to slow down. So when I draw my next velocity vector, I'm just going to draw it in the same direction. I'm going to draw it a little bit smaller, okay? All you're trying to convey to me is that you understand, wow, Burkamp, I know this person is getting smaller, so her velocity vectors are getting smaller, okay? So then, when you look at this, and she has positive velocity, and she's slowing down, you know you have to have negative acceleration. She cannot speed up with positive acceleration. So just come here and go, okay, hey, her acceleration vectors are going to be pointing in the opposite direction. And later on, you'll see that's going to tell us which direction the force is acting on her as well, but we'll get to that later. So literally, on 11A, that's all you have to have. You don't even have to draw the person, the stick figure, okay? Draw two velocity vectors and an acceleration vector. And your acceleration vector is either in the same direction, and your velocity vector is getting bigger, or your acceleration vector is in the opposite direction, and they're slowing down. That's it. Those are the only two things that you can do. Now, the next thing you want to do is you want to draw a graph. Okay, here's the velocity time graph. And you're going to start here at 4 meters per second. And again, only one of two things could happen. One of two things. Either this velocity vector slopes upward, and she's going to go faster, or that velocity vector is going to slope downward, and she's going to slow down. That's it. Only two things that can happen. Oh, right, she's going to stop. I'm going to bring this down like this. And that's going to take a half a second. Boom, that's all you have to do. That's it. That's all you have to have on your velocity time graph. Not make this complicated. Then, but you want to label the acceleration and a whole bunch of other things. So your acceleration, again, is just the rate at which your velocity changes. Okay, your acceleration is not how fast you're going. So, but again, look at this. Oh, all right, positive velocity. She's slowing down. You know your acceleration has to have a negative value. If you look at the graph, that line has a negative slope to it. Your acceleration vectors are pointing in the opposite direction. Oh, I'm going to have negative acceleration. Okay, so there's no way you can end up with positive acceleration. Okay, so then you go, oh, if you're a formula kind of person, you go A equals V minus V naught over time. Final velocity is 0, initial velocity is 4, time is 0.5 seconds. You're going to get negative 8 meters per second squared. Okay? So come in here and make sure that you label that slope. Oh, here's my acceleration, negative 8 meters per second squared. Now, when you get to D, right, on that one they're going to say, okay, how far did she slide before coming to a stop? There is a myriad of ways that you can answer D. One option is that you go to that velocity time graph and you find the area of that triangle. Oh, it's an area of a triangle, 1/2 base times height. So if you like finding areas of triangles, find the area of that triangle. That's an option. You go, oh, but Mr. Burkamp, I like equations. Fine. Distance equals 1/2 v plus v naught time. You know your final velocity, you know your initial velocity, you know your time, which is the exact same thing as finding the area underneath that graph, because that area underneath that graph is 1/2 base times time. It's the exact same calculation, okay? So you go, oh, Mr. Burkamp, I like using distance equals 1/2 at squared plus v naught time, okay? Now, you can use this equation to find the distance. I don't recommend it for two reasons. Number one, it's complicated math. You got t squares and you got v naught, and okay, you could do it, but it's just a lot of work. The more important reason why I don't recommend that you do use this equation is because you're using an acceleration that you had to find up above. And if that acceleration is wrong, then that calculated distance is going to be wrong, okay? So you can do it, it works, but you're rolling the dice, okay? You always try and want to use values that were given to you as much as you can. Okay, you will reach a point where you have to use other values, but just try and put that off. Now, when you get to E, how fast was she moving at 0.3 seconds into the slide? Okay, well, look at this. Here you are at 0.5. Here you are at 0.3. So you know your answer has to be somewhere between 4 and 0. Okay? Your velocity has to be somewhere between 4 and 0. So it can't be faster than 4, because that would be really weird. Okay? It can't be a negative number, because then you're saying that she's moving backwards at 0.3, but yet she ends up at the base, which is still really weird, because then she'd have to change directions, which would be really odd. So what I would recommend is you just go, oh, okay, v equals v naught plus at. It's a slope-intercept formula. You know your acceleration, okay, because you found that. You know your initial velocity is 4. You know the time is 0.3, okay? All you're finding is a y value that corresponds with an x value of 0.3. Okay, you are finding an x and y coordinate. 0.3, boom, there you go. Anyway, so if you keep that in mind, and like I said, the more ways that you can look at a problem, the better off you're going to be. Oh, this is an x and y system. I'm just finding an x and y coordinate that we're calling time and velocity. Okay, look at what your answer should be. Well, it's got to be somewhere between 0 and 4. And like I said, the more ways that you can look at a problem, the better off you're going to be. When you get to number 17, okay, so let's talk about 17, because there are some pitfalls on 17. So here's the story. You got a car moving at 20 kilometers per hour. The first thing that you have to do is change that into meters per second, which is like 5.56. We went through that yesterday. Okay? So again, first thing you want to do on 17 is draw some motion diagrams. So just come in here and go, here's V1, you're slowing down, there's V2, I got a negative acceleration. That's all you have to do. Okay? Do not make that complicated, literally. You draw your first vector. If you were speeding up, you draw your second vector bigger, and then you'd have positive acceleration. If you're slowing down, which in this case, you draw your second vector smaller, you point the acceleration vector in the opposite direction. Do not make this complicated. Now, draw motion diagrams, and then B, what is the value of the acceleration? If you look on this, if you do the V naught DAT chart, okay, you'll notice that there is no mention of time. Okay, there is no mention of time. So what's the only equation that doesn't involve time? That equation. So you know you're going to use that equation. So you can go, okay, v squared equals v naught squared plus 280. You know a distance, you know your initial velocity, you know your final velocity, solve the equation for acceleration, and then put in the numbers, okay? So go, okay, Mr. Burkamp, I can do this. I learned some algebra along the way in my misspent youth. Divided by 2d, I get an acceleration. Now, before you actually crunch the numbers, think this through. Is your acceleration going to be a positive or negative number? Devin,
It's going to be a negative number
why?
because it's stopping.
And your velocity is
Uh,
positive or negative?
it's positive.
Yeah. That's why you know you're going to have, if you end up with a positive acceleration, you've done something wrong. So, this is where you have to pay attention to what's your final velocity and what's your initial velocity. So my final velocity is going to be 0. My initial velocity is that 5.56. Don't forget to square it, okay? Don't forget to square it. And you know your distance, so that first acceleration is going to be something around -5 meters per second squared, okay? That's kind of a rough estimate of what your answer to 17B should be, something around -5, okay? Now, on C, I'm going to show you 2 ways you can work C. You have options. So, on C, you're going, how far would it take the car to stop while going from 40 kilometers to rest? Now, here's what you're tempted to do. You're tempted to do this. You say, well, if I was going 20 kilometers per hour, I stopped in 3 meters. Okay, so 20 kilometers per hour, I stopped in 3 meters. Well, now I'm going to go 40 kilometers per hour. If I double my velocity, I should double my distance, and it should take 6 meters. Okay, you're tempted to do that. Don't. Okay, because it's not a linear relationship. Okay, that's why you can't say, well, it's just going to stop in 6 meters. So one option that you can do is smash mouth physics, okay, where you put in numbers. Okay, I'm going to go back to that equation. I'm going to go v squared equals v naught squared plus 280. I'm going to start with that. Now I know my acceleration. I know what that value is. So I can go v squared minus v naught squared over 2a and get my distance that way. Okay, and it should work out to be about 12 meters. Okay, should get something around 12. So that's smash mouth physics, and it works. Okay, now here's the other way that's a little bit more elegant to do. If you look at v squared minus v naught squared over 2a equals distance. So here's the other way that you can do this. You'll notice on this one that your final velocity is getting doubled. Okay, it's getting doubled. So then if you look and go, well, my final velocity is still going to be 0, minus, then I'm going to have 2v naught squared over that same acceleration. So when you do this, this becomes v squared minus 4v naught squared over 2a. And then you realize, oh, well, if that's going to go up by a factor of 4 because it's squared, then my distance has to go up by a factor of 4. I'm going to go from 3 meters to 12 meters. Okay? That's a more elegant, kind of a philosophical, mathematical approach. But if you like that, it works to go, oh, okay, I'm going to be going twice as fast. That's the squared value. That's going to go up by a factor of 4. My distance will go up by a factor of 4. I'm going to go from 3 meters to 12 meters. So you can either do the smash mouth physics and do it that way, or you can look at the more mathematical approach. I don't care. Pick one. Pick the one that works best for you. Your answer to 18A, that acceleration should be something around -10. On 19, your distance should be between 60 and 70 meters. On number 20, A and B, both of your answers would make horrible GPAs. And the time would be a worse GPA than the acceleration. Okay? On the multiple choice, none of your answers should be C. If you have C on any multiple choice answer, you have done something wrong. Okay, is there anything else, any other problems that you want me to talk you through? Yes, ma'am.
Number 6.
6? Question 6? Okay. So, here's what you've got. So what I'm saying on number 6 is the displacement of a body is a quadratic function of time. All I'm saying is that if you draw a position time graph, you're going to get a quadratic function that's going to look like this. Okay, so it's going to be a curved line. So here's the story. Right away, I know I'm going to be accelerating because of the fact that this thing is curving and the slope of a position time graph gives me velocity. Okay? So I know right away I have to be accelerating. So right away, I can eliminate C and D. It can't be C or D. Because if the displacement versus time was a linear function, meaning that it's a straight sloping line on a position time graph indicating that you have constant velocity, then it could be C or D. But since it's a curved line, it cannot be a constant velocity or a constant speed, which leads me to A and B. Now, when you get uniform versus non-constant acceleration, look at this idea that distance equals 1/2 AT squared, okay? Which is basically what's going to generate that graph. So the only way this works is if your acceleration is the same all the time. If your acceleration is continuously changing, this is no longer a function, and you're going to get a line that's going to go, God knows what it's going to do. So that only works if you have uniform acceleration, because that's what allows you to graph. If you're in a math class, you'd call that y equals kx squared. Your k is just going to be a constant. So any quadratic function only works when you have a constant, which means you have to have the same acceleration, which is what we call uniform acceleration. Okay? Got it? Anything else? Going once, going twice, sold. So get that handed in. So can you stop that camera? Thank you, Joe. All right. So here's the next continuation, and this is the idea of gravity. Now, the beauty of gravity calculations is that all we're going to use is the exact same equations that we had before. So there isn't like a set of equations if a car is speeding up, and there's another set of equations if something is allowed to fall because of the influence of gravity. Okay, it's the exact same idea, right? So the beauty of it is all we're going to do is use the same 4 equations that we used on yesterday's assignment. The only difference when you're talking about gravity, because it's a very specific acceleration, instead of putting like just your basic acceleration, which might be like 4 meters per second squared, something like that, okay? When you're talking about gravity, we're going to use this lowercase g, which you all have done before. If you remember back to the very first lab that you did when you hung the weights from the spring, and I said, oh, Fg equals mg, okay? And I said, we'll explain what that g means later on. Well, today is that day. So, well, anytime, and you're on Earth, okay, this is going to be important, unless you are specifically told that you're on the moon or you're on Jupiter or someplace else, g is always going to be negative 9.80 meters per second squared, okay, which is that acceleration. So what that means is that if you drop a rock and you let it fall for exactly 1 second, and you start at 0, you drop it, okay, just like this, and you let that fall for exactly 1 second, that means that it's going to be going negative 9.8 meters per second at the end of that second. At the end of the second, it's going to gain another negative 9.8, which gets you like negative 19.6. So, for the sake of simplicity, on these calculations, we're always going to let g be negative, because we're going to define down as being negative and up as being positive in terms of velocity, acceleration, displacement. So anything pointing down is going to be negative, anything pointing up is going to be positive. So what we're going to do is we're going to look at two different situations. One where you drop something, and the other one where you throw it. Okay? So the dropping is simple. You hold it up, boom, you just let go of it. But what's going to be important when you drop something is that the initial velocity is going to be 0 meters per second. Now, if I throw it, I could either throw it up in the air like this and let it fall. I could throw it down. Doesn't make any difference. So that's going to be the fundamental difference. If you drop something, initial velocity is 0. If you throw it, V naught does not equal 0. And if you throw it up in the air, V naught's going to be a positive number. If you throw it down, V naught's going to be a negative number. Okay? You got to be able to work with both of them. And one of the key things we'll talk about is this Jedi-Stofa law. And that stands for stop the force and watch. So when I drop this ball, it begins to accelerate. So what that tells me is that there has to be a force acting on it, and that force is going to be gravity. Because Mother Nature doesn't like things to accelerate. Mother Nature likes the status quo. So when I drop this ball, and I begin to see it accelerate, I know that there has to be a force acting on it. Now, if I throw it down, throw it up in the air, as soon as it leaves my hand, the only force acting on it is still gravity. Now, when I throw it up in the air, hey, gravity is going to make it slow down at negative 9.8 meters per second squared. If I throw it down, as soon as it leaves my hand, gravity is still going to make it speed up at negative 9.8 meters per second squared. So as long as gravity is the only force acting on it, your acceleration is going to be negative 9.80 meters per second squared. Okay? You don't have to think about it like, oh, what is it going to be? Negative, maybe it's negative 10, maybe it's, no. It's going to be negative 9.8 meters per second squared. Now, there is a key assumption that we make. The key assumption that we make is that there is no air resistance. Because clearly, in reality, if I take this tissue paper and that golf ball and I drop it, okay, clearly there's different accelerations. But that gets real complicated in terms of drag coefficients and all that other stuff. So we're just going to make it simple. We're just going to assume that there is no air resistance and that acceleration is negative 9.8 meters per second squared. Okay? So unless I tell you differently, just go with G being negative 9.8. Now, the other thing in terms of displacement, here's the whole idea, and this is going to be true of both of these. Anything going up is going to be a positive value. Anything going down is going to be a negative value. But and you see how this will play out large later on. So if I drop this ball and I make this the reference point, then it's going to be moving away from 0 with negative displacement. If I make the ground the reference point, and the ground is 0, and then it's going to have some positive position up here, and then it's going to fall towards the reference point. So depending upon how you set this up, it's either going to go away from the reference point or it's going to go towards the reference point, depending upon how you set up the problem. Now, when it lands, okay, this thing is going to end up with some negative velocity, okay, because we're defining down as being a negative value, okay. Now, if I throw something up in the air, it's going to start with some positive velocity. Now, if I throw this thing up in the air, does it change direction? Yeah. Now, one of the key things, and you'll see this later on as we go work through some problems, when you throw something up in the air, when it reaches its maximum height, okay, at its maximum height, what's the velocity going to be? 0. Okay? So when you throw something up in the air, when it's at its highest point, that velocity goes to 0. Okay? And that's going to allow us to do some math that's pretty simple, that looks complex, but it's going to go to some 0 velocity. Okay. So we're just going to work through a couple of problems. So I'm going to have a golf ball, and I'm going to hold that golf ball 2 meters above the ground, okay? And I'm just going to drop it. 2 meters is about like 8. I'm just going to drop it. I'm not going to throw it. Not having a bad day. It's like, throw it down, throw it. I'm just going to drop it, okay? It's just going to get dropped. Okay? And that's all I know. It's going to height of 2 meters. I'm going to drop it. Just going to drop it. So what I want to know is a couple of things. I want to know how long it's going to take for it to land. And I want to know how fast it's going when it lands. Okay, so those are the two things that I want to know. I also want to draw a velocity time graph. And then I want to draw a position time graph. Okay? Two things that we want to do. Now, what I'm going to do in this situation, and you'll see that you get the same math either way, I'm going to make the point that I let go of it my reference point. Okay? I don't have to make that the reference point. I can make the ground the reference point. That's also valid. But I'm just going to make the point where I let go of it. That's my reference point. Boom, 0. Now, here's what's going to be important. That's going to be 0 meters. Okay? So what that means, then, if I'm defining down as being a positive value, when it hits the ground, then my position is going to be negative 2 meters because it's just like a number line. Here's 0. Anything below that point is going to have a negative position, which is going to be negative 2 meters. Okay. Now, what that means, though, is that when I draw my position time graph, I'm going to start that at 0 meters because that's what I'm calling my reference point. And then I'm going to define down as being negative values. So I'm going to end up down here at negative 2 meters. Okay? And we'll get to what that graph's going to look like in just a second. But my position time graph is going to start at 0, and it's going to end up down at negative 2. We got that. Okay. Now, let's talk about the velocity time graph. Connor, where's my velocity time graph going to start?
0.
0. I'm just going to drop it. Okay? If I threw it down, I would start with some negative velocity. If I threw it up in the air, I would start with some positive velocity. But I'm just going to drop it. Boom. There you go. Now, I'm going to give you 6 different options. Count them, 6 different options for what the velocity time graph is going to do. You can have an upward football like this, or we can have a downward football like that. Okay? So, upper, middle, lower, upper, middle, lower. Which one do you think is right?
Negative.
Huh?
The negative middle one.
Why?
Because it has negative velocity and it's uniform acceleration.
And what's the value of that acceleration vector?
Negative 9.8 meters per second squared.
Fantastic. Good. We know the acceleration is negative 9.8 meters per second squared because that's what we said it was. Oh, it's going down. We're defining that direction as being a negative value. So it can't be anything up on the top side because that shows the fact that, oh, it's speeding up with positive velocity. So it couldn't be any of those. Now, the reason that it's that boring middle line is because gravity is boring. Okay? You drop it. Oh, gravity goes, all right, fine. We're going to make a very specific acceleration of negative 9.8 meters per second squared. So when something is under the influence of gravity, and this is going to be important, and that is the only force acting on it, if that is the only force acting on it, nothing else, that slope of that line is always going to be negative 9.8 meters per second squared. Okay? You don't have to think about it. Say, oh! Now, if I'm on the moon, that's going to become a much more shallow slope because the gravity on the moon is negative causes an acceleration of negative 1.63 meters per second squared. If you're on Mars, you get an acceleration of about negative 3 meters per second squared. Okay? So the Earth has a relatively big gravitational field, which is cool because that's what allows us to have an atmosphere, and without an atmosphere, we wouldn't be here having this discussion. Okay? So it's fairly important that we have such a strong gravitational field, or we wouldn't be here. All right. Now, so this is what my velocity time graph is going to look like. Going to start at 0, boom, it's going to speed up. Now, let's go back to the position time graph. Izzy, which one of those lines is my position time graph curve? Upper lip, middle lip, lower lip?
The lower.
Lower. Why?
Because, oh no, never mind.
Good.
The middle one?
Nope.
Oh shoot, the top one.
Top one. Oh, I had such high hopes when you said, no, it's not the bottom. I was like, oh, she's going to pick the top one. No. Okay,
Nope.
now, why can't it be the middle curve? What does the slope of your position time graph give you?
It gives you velocity. but
So if
it's
it's
not-
if it was the middle lip, what would happen?
it would just stay accelerating. Or the acceleration would not change.
The velocity wouldn't change.
Yeah, and the acceleration would.
Yeah, so you would drop it and it would just fall at a constant rate like this, if it was the middle curve, okay? Now, the bottom curve would be cooler to watch, because the bottom curve would mean that it starts off really fast and then it slows down right before it hits the ground. Okay, you drop it and it goes, whoo, and then it would slow down right before it hit the ground. It's cool to watch. Probably not going to happen. Now, Izzy, why is it the upper curve?
Because it has uniform acceleration.
And more importantly, what is the upper curve doing? Is it showing speeding up or slowing down?
Slowing down. Or speeding up.
Yeah, because it starts off shallow, right? So we start off with some small negative velocity, and then as it falls, those tangent lines are getting steeper and steeper and steeper. So that's why it's going to be that curve up there. Okay. So after much trial and tribulation, we know what our position time graph is going to look like. That's going to be, dogs. There we go. And that's, oh, would you stop? That's going to be at -2 meters. Got my position time, got our velocity time. Here's my V1, okay? My initial velocity vector. Adana, as that thing falls, what's going to happen to the magnitude of that velocity vector? Is it going to get bigger or smaller? Bigger. So if I ask you to do that, I'm going to go V2, it's going to get bigger, okay? So since it's accelerating downward, and my velocity vectors are getting bigger, okay, which direction is my acceleration vector going to point? Downward or upward? Hector,
Downward.
what'd you say?
Downward.
Downward. So I'm going to have some negative acceleration. And as soon as my acceleration vector points in the same direction as my velocity vector, I'm going to speed up. So now, here's what I want you to see. We've painted the big picture. We've figured out what the position time graph is going to look like, what the velocity time graph is going to look like, and we know the direction that my velocity vectors are changing. We know the acceleration vector is going to point downward. We have all this stuff. Now we can tackle the mathematical side of it, because now we've painted the big picture. Okay, so the first thing I want to figure out is how long that it's in the air. So let's do the how long. Okay, so let's do the v-dat chart. So my final velocity, I'm going to find that later on. I don't know that right now. I know my initial velocity is 0 because I was told that I'm just going to drop the ball. Okay, so my initial velocity is 0. My distance for now, I'm just going to put that as 2 meters. Okay, for now I'm just going to put that as 2 meters. My acceleration, we said, was negative 9.80 meters per second squared. And my time is what I don't know. Okay? So, I don't know my final velocity. I know my initial velocity is 0. I know how far it's going to fall. I know my acceleration, and I need to find time. So, look at your 4 options. Okay? So, what equation is going to allow you to find the time? So, right away, since I'm trying to find time, would I want to use that equation?
No.
No, because it doesn't involve time. So right away, that equation is out. Okay? I could try and use v equals v naught plus at. That involves acceleration. But I have 2 unknowns. I don't know time, and I don't know my final velocity. So that's out. So what's the only equation that doesn't include the final velocity? It's the only one that doesn't have final velocity in it. Evelyn.
Distance equals velocity initial times time plus 1/2 acceleration times time squared.
Beautiful. Okay? 1/2 at squared plus v naught time. That's a great equation. Now, here's the beauty of this one. Because we dropped it, okay, because we dropped it, that whole thing goes out. Okay, I don't have to worry about it because it's going to be dropped. Okay? Now, this is a wonderful concept, using this equation when your initial velocity is 0. Okay? Could be a car starting from rest, it could be a dropped ball, doesn't make any difference. It's a great little equation. And we need to solve that for time. Okay? So, Tyler, what does that equation look like solved for time? I hate fractions. Let me give you a hint. It rhymes with multiply by 2.
You multiply by 2.
Very good. Then what? So now I got that. That whole thing's gone. I need to get time by itself.
You would divide over acceleration.
Yep. Fantastic. Then I need to get rid of that square root, or that squared function.
It is square root.
Yeah. Was time. Now, this is a great little equation. Embrace it. Use it. It's wonderful. It saves you a lot of heartache. But the caveat is that it only works if your initial velocity is 0. Okay? So if I throw this ball up in the air, I can't do that. If I throw it down, I can't do that. But if I drop it, then it's a cool thing to use. Now, what I'm going to do next is wrong. Okay? It's wrong. Do not do what I'm about to do. Do not do this. So, okay, this is not a big deal. Height is 2 meters above the ground. Acceleration is negative 9.8 meters per second squared. Okay? So, for those of you that are math nerds, why is this problematic at this point? You have a negative underneath the radical. Okay? So it's the only way to handle negatives underneath the radical.
Imaginary numbers.
Imaginary numbers. Okay? So we're going to have imaginary time. It's like, well, that's kind of cool. Not really. Okay? Physics doesn't do well with imaginary times. Okay? So at this point, you have a couple of options. The easiest option is that you, almost dropped my banjo. The easiest option is that you just ignore that and make it a positive 9.8. Problem solved. Boom, there you go. Or we'll just cover it up. That it's not there. There it goes. Not a big deal. Simple. Okay, just ignore it. It's like if your car is making like a weird noise, just turn up the radio. The noise will go away. Okay? I don't recommend it, but the noise goes away. It's like, did you fix your car? No, I just turned up the radio. Okay, cool. Don't recommend that. So we can't do this because we have to work these problems holistically. We have to view them as one big concept, okay? We can't nitpick and go, well, maybe we'll make it negative. Oh, that's annoying. Let's make it positive. But this is why you work this problem from a big picture standpoint. And you go, yes, I do have a negative acceleration. But if you go back up to your position time graph, okay, I landed at -2 meters because I defined my point of release as being 0, and anything going down is going to be a negative value. Oh, okay. Now if I look at my displacement, remember displacement is position final minus position initial. Oh, if I take -2 meters, which is my final position, minus 0, which is my initial position, check my math, I should get -2 meters. Oh, that's cool. Okay? Now look what happens. Now I have 2 negatives underneath the radical. Now that becomes a positive value. Okay? And now y'all are teenagers and you sit back going, Bergkamp, dude, chill out. Okay? It's a negative sign underneath the radical. Just ignore it. Come on, man, chill out. No. And here's the reason why. If the sooner you embrace this idea that you look at these problems when it's one big unifying theme. Oh, I have negative acceleration. Oh, I'm going to have negative velocity. I'm going to have negative acceleration. If you start to like piecemeal it and just ignore things, it's going to end up being a train wreck. Okay? You have to look at these problems from a big picture perspective. Now I do have 2 negatives underneath the radical. 2 negatives underneath the radical produces a positive value. Hey, I'm off to the races. So somebody take their calculator, and here's what you're going to do wrong. You're going to be all excited, and you're going to take 2 times 2, and you're going to get 4, and you're going to divide that by 9.8, and then you're going to forget to take the square root. Okay, promise you, this is what's going to happen. You're going to forget to take the square root of this. And you go, Mr. Bergkamp, we won't do that. It's like, you lie. Anyway, so somebody take 4 and divide it by 9.8 and then take the square root of that. Nathan, what'd you get?
0.64 or 0.638.
0.638. Okay? So, and we can test this. Okay? So if I hold this up to a height of 2 meters and I drop it, I should be able to time that and see if it matches 0.638 seconds. If it does, we did all right. So if we very crudely do this, I'm going to let go 1 Missa, okay? So if you consider 1 Mississippi being 1 second, if I hit 1 Missa is 0.638 seconds if you do the conversion, okay? So it worked beautifully, okay? So 1 Missa is exactly 0.638 seconds. I took a class in this conversion. I got it. Okay. So we're cool, right? Now, let's talk about the velocity at impact. I need to figure out how fast it's going when it hits the ground. Now, don't tell me it's 0. Oh, velocity is 0 because it hits the ground. No. It's not it, okay? We need to figure out what the velocity is at the point of impact. Now, I want you to think this very carefully before you answer this question. Very carefully. I'm going to fall for 0.638 seconds. Is my velocity at impact going to be exactly negative 9.8 meters per second? Less than negative 9.8, like maybe negative 6, negative 5, negative 4, something like that? Or is it going to be bigger than negative 9.8, like maybe negative 10, negative 11, negative 12, something like that? So those are your 3 options. The velocity is going to be less than negative 9.8, like negative 5, negative 6, something like that. Exactly negative 9.8, because that's the acceleration due to gravity. Or because it's falling and speeding up, it's actually going to be bigger than negative 9.8, like negative 11, negative 12, something like that. So how many think it's going to be less than negative 9.8? Okay. How about equal to negative 9.8? Nobody's on that one? Greater than negative 9.8. Thank God. Okay. Hey, why is it going to be less than negative 9.8? No, you didn't change direction, it fell in one, it only fell in, one direction. It's not the reason why. It is less than negative 9.8, but that's not the reason why. Devin,
Because it hasn't had time to fully like accelerate. It hasn't had time to speed up yet.
as soon as I let go of it, it begins to speed up.
But it would take a second to get to negative 9.8.
Ah, there's your answer. That's the answer that I'm looking for. Remember, acceleration is the rate at which your velocity changes. So if you look on your velocity time graph, if you start at 0 meters per second, if you go over 1 second, you're going to go down negative 9.8 meters per second. That's what that acceleration means, okay? So this is why when I draw that velocity time graph, it was a straight sloping line with a slope of negative 9.8 meters per second squared. So if this ball fell exactly 1 second, it's going to be traveling exactly negative 9.8 meters per second when it hits the ground, okay? If it fell exactly for 1 second. But we don't fall for 1 second. We fall for like 0.638 seconds. So I know my velocity has to be less than negative 9.8 because I fell for less than a second. Okay? That's the answer that you got to. And that's a wonderful thing. Okay, now let's talk about the velocity at impact. There's a couple of ways you can do this. One option is that you can go v equals v naught plus at. You know your acceleration, you know your time is 0.638 seconds, and you know the initial velocity is 0. Okay? You can do this. It's wonderful. Okay? But what's the downfall of using that time? You had to calculate it. If my time is wrong, that velocity is going to be wrong. So is there a way to calculate time, a way to calculate the final velocity without using time? What? What could I use? Oh, I can use that equation. V squared equals v naught squared plus 2AD. It's cool. I can do this. What's my initial velocity going to be? 0. I know my acceleration. The only thing I don't know is my final velocity. Now you have to be very careful on this one. So v then is going to equal the square root of v naught squared plus 2AD. Now, what I'm going to do is wrong. Okay? Do not do what I'm about to do. It's wrong. 0 squared, that isn't what's wrong. That isn't the bad part. Okay? So if I do that, what's going to be the problem? I've got a negative underneath the radical, and I'm going to have imaginary velocity. Okay? If you ever get pulled over by a cop and he says, you know how fast you're going to go? Oh, I don't know. I have an imaginary velocity. I have negative. I'm taking the square root of a negative value. You're going to end up in jail, I promise you. Cops have no humor when it comes to imaginary velocities. So, how can we, so again, can we just ignore the negative 9.8? No. But what's my displacement? Negative 2. Oh. Now I have two negatives underneath the radical. Winner, winner, chicken dinner. I get this. Now, this is where your calculator is going to lie to you. Okay? Calculator is going to lie to you. Do the math and then tell me what your calculator says the answer is. Actually, it doesn't lie. It just doesn't tell you the whole truth. So what do you get as that answer? 6 point something, I think. Devin, what'd you get?
6.26.
Meters per second. Now, speed, you're okay. Because speed doesn't have a direction. Speed is, how fast is it going? 6.26 meters per second. But technically we want velocity, okay? Technically we want velocity. But what's the square root of 4?
2.
Or,
-2.
oh, so since we want the velocity, what do we have to do? It's still 6.26, but we just choose the negative root, okay? Because it's a square root. So it's a plus or minus value, you just choose the negative root. So the advantage of this method is that it goes off of known values. The disadvantage of this is that you have to choose the negative root. Now, if you look at V equals V naught plus AT, now, the advantage of this one is that it will automatically give you, and you use that time of, what was that time? 0.638 seconds, go away. 0.638 seconds. So the advantage of this one is that it will automatically generate a negative velocity, so you don't have to worry about choosing the negative root. The disadvantage is that you're using a time that you found up above, okay? So it's, you roll the dice. They both have their advantages, okay? Do I choose a negative value? Do I not? Do I, it's whatever works for you. So if you're feeling good about that time, you can use that, okay? But if you're going, oh, I don't know, okay? Then go to that equation. That way you don't have to worry about time. Okay, stop that camera for a second. We have one big. On this one, we're going to take the ball and we're going to throw it up in the air, and Carson picked 22 meters per second. Okay? That's the only number that we know. It's 22 meters per second. From that one number of 22 meters per second, I want to find the time up, the time down, the total time, the maximum height, the velocity and height at 1 second, the velocity and height at 2 seconds. I want to draw the position time graph and the velocity time graph, and we know one number, and that's 22.0 meters per second. We want to find all of that from one number, okay? But are there some other numbers that we know that we didn't necessarily write down? What's another number that we know? We know the acceleration, okay? We're assuming we're on Earth, right? So hidden within this, if you look at V naught dat, okay? So we know the initial velocity is going to be 22.0 meters per second. We know, as Angel said, my acceleration is negative 9.80 meters per second squared. Okay, so we got that. Now, let's talk velocities. Let's talk velocities. When I throw this thing up in the air, and it reaches its maximum height, okay, this is going to be important. When it reaches its maximum height, what's the final velocity going to be?
0.
0. Ooh. Now, that's going to be 0 meters per second. But that's only going to be at maximum height. Okay? It's going to go from 22 to 21 to 19.8. All of this things in between. But that's going to be a critical value. When it's at its maximum height, final velocity is going to be 0. Okay, got that going for us. So let's go down and tackle the position time graphs. So what we're going to assume is that the point that I let go of it is going to be the reference point. We could make the maximum height the reference point, but it's going to make life god-awful complicated. Let's just not do that. So I'm going to make the point that I let go of it the reference point, and then we're also going to assume that it's going to come back to the same point. Okay, so I'm going to throw it here. I'm going to catch it back at the same point. So, what's my position time graph going to look like? I'll give you 3 options. This one, that one, upper lips, middle lips, bottom lips. Carson,
The top.
top lip,
Yep.
solid on that one. Solid on the top lip.
Yep.
Yes, Mr. Burkamp, I am absolutely solid on that top lip, and you should be. Okay. Why the top lip?
Because at the beginning when you throw it, it's gonna be it's steeper, so it's its fastest
Fantastic.
acceleration.
Keep going, girl.
And then it'll start to shallow out and hit zero once you hit the top.
Fantastic.
And then it'll start to accelerate again when it starts to fall down.
Spot on, perfect explanation. Well done. So you're going to start off with positive velocities, okay, that are really big, okay. Now, at time zero, here's an interesting question. If you go to time zero and you drew that tangent line, what would the slope of the tangent line be at time zero? No. At time zero, if you were to draw that positive sloping tangent line, Carson, you pick the number,
Oh, 22.
22 meters per second, right? So that initial tangent line on your position time graph is going to have a slope of 22 meters per second, because that's how fast it was going when you threw it, okay? And then it's going to shallow, get slower, and then it's going to reach a velocity of 0. Now, when it has that velocity of 0, that's when it's going to be at its maximum height, and then you're going to get some negative velocities coming down like this. Now, here's an interesting idea. When it lands back in my hand, listen to me very carefully what I'm going to ask you. What's the velocity of the ball when it lands back in my hand? Nope. What'd you say? Not 22. Close.
9.
Huh?
What were you wrong again?
You need to put one word in front of the 22.
Negative.
Ah! So when it lands, it's going to have a velocity of negative 22 meters per second. Now, listen to me very carefully on this one. What's the speed when I throw the ball? 22 meters per second. What's the speed when it lands? 22 meters per second. Because speed is just a scalar quantity. It's how fast you're going. It doesn't have anything to do with direction. So I throw it at 22, it lands at 22 in terms of speed. The velocity goes from positive 22 to negative 22. Okay? And you can do that as long as it's symmetrical. So, the velocity time graph. Miss Elliott, where's my velocity time graph going to start? What'd you say? Positive what value? No. Okay, you're just seeing if I was paying attention. Okay, did I pass?
Yep.
Okay, fantastic, good, okay. 22 meters per second. Now, what's that graph going to do? Curve or straight? Curve or straight? Curve or straight? Straight, why?
Because it has uniform acceleration.
It has uniform acceleration. And, Miss Elliott, what is the value of that uniform acceleration?
-9.80.
Fantastic, because we're on Earth, okay? Our strange rock has this great gravitational field, okay? It allows us to have an atmosphere. It's cool, right? Now, where's the ball going to be at that point when it crosses 0? There's 0 meters per second. Where's it going to be? Max height, right? Because that's when the velocity goes to 0. Ooh! At that point, you are at maximum height. How cool is that? That's nice. Okay. Now, we have all of this going on. We're going to start with some positive velocity of 22 meters per second. as the ball goes up, what's going to happen to the magnitude of that velocity vector? Bigger or smaller? Smaller. It's going to get smaller. Because oddly enough, if this is V1, V2 is going to be smaller because we're going to have a negative acceleration. On the way down, what's going to be the sign of my velocity? Positive or negative? On the way down, what's the sign of my velocity? Negative. Okay, because we changed the direction. Oh, all right, we changed the direction. So on the way down, here's going to be my V1. It's going to have some negative value. Here's my V2. That's going to have a big negative value. That's going to be getting bigger. Now, on the way down, listen to me very carefully. On the way down, do my velocity vectors change sign? On the way down, do my velocity vectors change sign?
Yep.
Yes, no one should hesitate on that answer. You should be going, solid, boom, change direction. No, it's going to change sign. One positive, negative. Should not give you any hesitation whatsoever. But are my acceleration vectors going to change sign?
No.
Will my acceleration become positive on the way down? I'm speeding up. No. Why?
Because you have to have the same sign since it's speeding up.
Ah, okay. Yeah, that's what everybody tends to screw up. Y'all want to make acceleration positive on the way down, okay? Because it's speeding up, and in your minds you harbor this misconception that positive acceleration means that you speed up, okay? And negative acceleration means you slow down. And negative acceleration does mean that you slow down on the way up. But I can speed up with negative acceleration because now my acceleration vectors are going to point downward because that's going to make my velocity vectors get bigger, pointing downward. Okay? That's also why my velocity time graph has the same slope the entire time of negative 9.8 meters per second squared. Okay? Now, F equals ma. That's the other reason we maintain the acceleration, same acceleration the entire time. As soon as it leaves my hand, what's the only force acting on it? Gravity. That force isn't going to change, the mass isn't changing, therefore the acceleration isn't changing. Okay? Now, so let's say that's the graph for Gary the golf ball. Okay? Gary the golf ball, I throw Gary the golf ball up 22 meters per second, comes back down. Hank, golf ball, Hank bowling ball. I'm going to take Hank, and I'm going to throw Hank up in the air at 22 meters per second. If this is the line for Gary the golf ball, what would the line look? What would the line look like for Hank?
Smaller. It'd just be like lower.
It'd be smaller.
It would be shorter. It wouldn't go as high.
Like
It wouldn't go as high. Wouldn't go as high. So maybe my velocity time graph would look
Velocity.
Oh yeah, I was not.
something like that.
And
Are you
velocity
starting at
one would
22
be
still?
Huh?
Are you still at 22?
I'm still at 22.
the velocity. Okay, it would be the same.
So it would still start up at 22?
Yeah.
No, did you throw it
I did.
all the way to 22?
I threw it at 22 meters per second.
All right.
Exact same. Yeah,
Same.
exact same. Here's the reason why. Look at look at the equations that you have. First 4 equations that you have. Where could you insert mass into that equation? Into the first 4 equations that you have. Where does mass go in those equations?
Nowhere.
Nowhere. Nowhere. So whether it's Gary the golf ball, Hank the bowling ball, if I throw them at the exact same speed, they're going to go to the exact same height, they're going to take the exact same time, everything's going to be identical. Now, is it going to take me more force to throw Gary? Or excuse me, to throw Hank? Oh yeah. Take a lot more force. It's going to be harder to throw Hank. because Hank has a lot more mass, okay? But when it's in the air and the only force acting on it is gravity, gravity doesn't differentiate. Gravity makes everything accelerate at the same rate, okay? So if I jump off this table and Carson jumps off that table at the exact same time, we're going to end up with the exact same acceleration. It's same acceleration of negative 9.8 meters per second squared. Got it? Good? Great. Okay, now let's talk numbers. Oh. Okay. So let's go back to where we started. We need to find the time up. Now, let's talk time up. V naught is 22 meters per second. Time up. Is my time up, I want you to think this through before you even answer it. Is my time up going to be bigger or smaller than 1 second? Or exactly 1 second?
Exactly 1 second. I'm just kidding.
Okay. You were just seeing if I was paying attention. I appreciate that. I always like to be kept on my toes. Twinkle toes Perkins, that's what they called me back in high school. Not really. Okay. More than 1 second, less than 1 second. Those are your two options. Less than? Less than 1 second. How many vote less than 1 second? Okay, no, stop. Let's say I threw the ball at exactly 9.8 meters per second. And we have an acceleration of negative 9.8 meters per second squared. If I threw it at exactly 9.8 meters per second, at exactly 9.8 meters per second, how long would it take for it to go to 0? Exactly 1 second, right? Because this is what that acceleration means. That's how much the velocity changes. Now, let's look at it this way. We're going to go to the mall, okay? We're going to go to the mall. And mom and dad are going to drop you off at the mall, and they're going to go, here's the rules. You're going to go into the mall. You have to spend $10 per second, every second that you're in the mall, okay? So if mom and dad gave you $10, you walk in the mall. How long is it going to take you to run out of money? 1 second, because you have $10 and you're going to spend $10 per second, right? Okay? If mom and dad gave you $20, how long would it take for you to run out of money? 2 seconds. Right. If you rounded the acceleration due to gravity up to 10, so round it up to 10, let's make the math easy. If the Earth was a little bit more massive or a little bit smaller, acceleration due to gravity would be 10 meters per second squared. So we're going to approximate it. You have $22 in your bank account. How long is it going to take you to run out of money? A little over 2 seconds, right? So if I throw this ball at 22 meters per second, guess what? It's going to take more than 1 second because my initial velocity was more than 9.8 meters per second to start with. Okay? So if you approximate it, it's going to take about 2.2 seconds. If you take 9.8 or 22 and divide it by 10, you get about 2.2. Okay, so if we actually want to get the numbers, you know V equals V naught plus AT. Do you know your initial velocity on the way up? 22 meters per second. What's your final velocity when you reach maximum height? 0. You know your acceleration, negative 9.8 meters per second squared. What's the only thing you don't know? Time. So if you go V minus V naught over A, you get time. Ah, that's kind of cool, right? So, Devin, take 0 minus 22 meters per second, and I'm going to do this wrong, and I'm going to divide by 9.8 meters per second squared. Now, why is that going to be a train wreck? If just divide by 9.8. You're going to get negative time, which is really weird and strange. Okay? If you ever get negative time, you have done something horribly wrong. But if I divide by negative 9.8 meters per second squared, ooh, now I get positive time. So Devin, what'd you get?
2.24.
2.24 seconds. And that's what we said matches. Oh, right, cool. My velocity was bigger than 9.8 meters per second. It was about 22. We kind of approximated it. Should said in about 2 seconds. 2.24. It's cool. Now, if we go back to my velocity time graph, I'm going to clean that up. I'm just going to start over. Here's my velocity time graph. You started up here at 22 meters per second. Doink. Here you are at 2.24 seconds. That's when that velocity is going to go to 0. So if it took 2.24 seconds to go up, how much time do you think it takes to come back down? Same amount of time. As long as it returns back to the same height. That's a huge caveat. If it returns back to the same height, it's going to take 2.24 seconds to come down. So that's going to put us out here at 4.48 seconds, which is going to be our total flight time. Okay, we got that done. No worries. So we've done all this. We've done the time up, the time down, and the total time. Now, let's talk maximum height. There's a couple of ways you can find maximum height. One option is that you go, oh, Mr. Burkham, man, I love triangles. You could use your velocity time graph. You can find the area on that velocity time graph. You know the base is 2.24 seconds. You know the height is 22. You could use area equals 1/2 base times height. If you're into area, you can do that. I don't recommend it because if your time is wrong, then that calculation is going to be wrong. You could go, oh, Mr. Burkamp, how about we do this? I like that equation. I like squared times. Good for you. You could use this. You could plug in 2.24 seconds because you know that's how long it's in the air. You know your initial velocity is 22 meters per second, and you know the time, and you know your acceleration's negative 9.8 meters per second squared. You can do this. It's cool. It works. But again, if your time is wrong, that maximum height is going to be wrong. But it works, okay, because this is like a function equation, and it works. How can I find maximum height without time? I can use that equation. Oh, v squared equals v naught squared plus 2ad. I have everything except for my maximum height. So I can go v squared minus v naught squared over 2a equals d. So somebody take 0 squared minus 22 meters per second squared divided by 2 times negative 9.8 meters per second squared. Let me know what you get. God, that was the longest sneeze. Oh. Okay, what'd you get? Now that I can see it, assuming I haven't like severed a blood vessel in my eye. What'd you get?
24.69.
Okay, call it 24.7 meters. Okay, well, it's a pretty good shot. Okay, this ceiling is like 2.5 meters, so if that ball would go up there quite a ways. So now we have our maximum height, and if you wanted to, you could always verify it. Go back and find that area, see if that's pretty close to 24.7. So you have a variety of ways that you could check that answer. Now, in the name of time, let's talk about, now we've got this, the velocity and height at 1 second and the velocity and height at 2 seconds. Now, there's only one way you can do these, to find the velocity and height at 1 second. There is no other option. The only way you can do this to find that velocity is to use v equals v naught plus at. Okay? And that should make sense. Oh, it's a linear function. I'm starting up here at 22 meters per second. This line is coming down like this after 1 second. Now, think about this in terms of the mall. You're at the mall. Mom and dad send you to the mall with $22. And they're saying for every second that goes by, you have to spend $9.80. So at the end of 1 second, you've spent $9.80. Take 22, subtract 9.8. That's how much money you have left, because that's how much money you have to spend every second, if you want to think of it that way. Or it's just a function equation. It's a linear function plus negative 9.8 meters per second squared. Plug in your time, plug in 1 second, plug in 2 seconds. There you go. So with this, you can find the velocity at any point in time. The only thing that changes is what you're going to put in there for that value of time. Now, to find the height, there is only one way you can do this. And that's doing 1/2 at squared plus v naught time. You know your acceleration, you know your initial velocity, plug in your values of time. That is the only way you can do this. It's a function equation. You plug in the different values of time. Okay. There we go. Actually got some purple paper back, so I'm excited to use that. It's the little things that make a difference when you're a teacher. Okay, so let me kind of get you started on some of these. 1 through 4 has nothing to do with gravity. Okay, 1 through 4 are old school equations. Don't use gravity. 5 through 13, now you're going to talk about gravity. So when you get to question number 5, just to make sure everybody's cool with how I want this done, okay, here's a bridge, and I'm going to drop a rock, a freshman, a bowling ball, whatever it is, okay? And you're going to figure out how far it's traveled at the end of 1 second, 2 seconds, 3 seconds, and how fast it's going. So that everybody's on the same page, I'm going to make that point of release the reference point, and that's going to be 0. So any velocity and displacement that you find on number 5 are going to be negative numbers, okay? They're going to be negative numbers. So you can use like distance equals 1/2 at squared plus v naught time. You're going to drop it. Your initial velocity is 0. You're going to have an acceleration of negative 9.8 meters per second squared. Plug in 1, 2, 3, 4. There you go. Okay, when you get to number 10, cannonball is fired straight up, initial velocity 24.6, calculate the maximum height. When you see maximum height, velocity is going to be 0. When you get to, where's it at? The one with the, on the back side. Number 14, on the back side. When you want to find how high is the border at this point, on 14A, do not use that equation. Mainly because you don't know which route to choose, the positive or negative value. So on 14A, you want to use distance equals 1/2 at squared plus v naught time. Okay? Do not use that equation on 14A. Okay. Have a good weekend. And by the way, the test over all of this is going to be on Wednesday. Okay? There's no new equations to learn. So we've got like this last big assignment on Monday, review on Tuesday, test is going to be Wednesday. So big test on Wednesday, which will be great because it's right before parent-teacher conferences.
I won't be.
Okay. Really?
Yeah.
Could you take it Tuesday after school?
Did I?
Yeah.